Dear students, we all know about diamond. Daily we are writing with pencil, and diamond we are using in jewelry. When we write with pencil, it leaves its mark. Have you ever think, is there any similarity between diamond and graphite? No? No, there is similarity between diamond and graphite. They are both the forms of carbon. They are known as allotropic forms of carbon. Now what is this allotropy? This is today's topic. Allotropy is the phenomena of existence of an element in two or more different physical forms which are almost chemically same. Allotropic forms have different physical properties but almost similar chemical properties. Many elements shows allotropy, but the most common examples are carbon, phosphorus and sulfur. Today we will deal with the allotropic forms of carbon. Carbon shows two allotropic forms, crystalline and amorphous. The crystalline forms are diamond, graphite and recently discovered fullerenes. They all have well-defined structure. Amorphous forms are coal, coke, animal charcoal, wood charcoal and lamp black. Let's discuss each one of them one by one. Diamond. Diamond is the crystalline form of carbon. It is denser than graphite. Its density is 3.514 grams per centimeter cube. It is the hardest substance known. It is a bad conductor of electricity and extremely chemically unreactive. All these properties are due to the structure of diamond. Diamond has a network structure. Each carbon in diamond is sp3 hybridized and it is tetrahedrally bonded to 4 carbons. Now we can see that in the center of the tetrahedron there is a carbon, and this carbon is attached to the 4 carbons via covalent bond. And at the corners of the regular tetrahedron there are other 4 carbons. This carbon-carbon bond length is 154 picometer, and this unit is the repeating unit. It repeats itself in the 3-dimensional space and we get a strong network covalent structure of the diamond. And due to the strong covalent bond, diamond is extremely hard and it has a very high melting point. All the valence electrons in the carbon are strongly bonded via carbon-carbon bond, and there is no free electron. And since there is no free electron, diamond is a bad conductor of electricity. Now we'll study about graphite. Graphite, another allotropic crystalline form of carbon. Its density is 2.226 grams per centimeter cube, lesser than diamond. Graphite is soft, has lubricating properties. It is a good conductor of electricity and is reactive. Now again, all these properties of graphite will be explained through its structure. In graphite, each carbon is sp2 hybridized. It is bonded to 3 other carbons in one plane, and this plane makes a hexagonal ring. It makes a hexagonal ring like this, and on each carbon there is one hybridized p orbital, and this p orbital, the half lobe, is above this plane and the other half lobe is below this plane. Now it is the situation of each carbon and they all form a hexagonal ring. These hexagonal rings now form a layered structure. This you can see from here. These layers are interconnected through van der Waals forces. These are weak forces which I have shown through this white tube. This is not a bond, this is only weak interactions. The fourth electron on this carbon, it forms a pi electron cloud and a pi bond which is above the ring and below the hexagonal rings. The array of the rings form the layers and the carbon-carbon single bond length is 141.5 picometers, which shows that it is a very strong bond. The layers are separated by a distance of 340 picometers, and these van der Waals forces, they hold the layers. Due to the weak van der Waals forces, graphite is soft and slippery in nature, and it is used as a solid and dry lubricant. You can compare it with when while playing carom you sprinkle talcum powder on the carom board. Normally, graphite is used as a lubricant in the heavy machinery. Since these bonds, these pi electron cloud is above this ring and below this ring, these are free to move and they are delocalized. So, graphite is a good conductor of electricity and it shows reactivity. Now, next allotropic form, crystalline form of the carbon is fullerenes. It is a new family of the carbon allotrope. It is discovered in 1985. H.W. Kroto, R.F. Curl and R.E. Smalley discovered it. They were awarded Nobel Prize in 1996. Examples are C32, C50, C60, C70 and it goes up to C350. Structure of C60. Known as Buckminster fullerene, they are also known as buckyballs. Preparation. C60 is synthesized by passing electric arc between the graphite electrodes at about 3773 Kelvin in the presence of the inert atmosphere of helium or argon. C60 is a perfect sphere. It looks like a soccer ball. It's highly symmetrical. It consists of 5 and 6-membered carbon rings. All carbon occupies identical position. 20 hexagons and there are 12 pentagons. I'll show you later on this PowerPoint slides. The 6-membered rings are fused both to other 6 and 5-membered rings, but 5-membered rings are connected to only 6-membered rings. The carbon-carbon bond length is 145.3 picometers and carbon-carbon double bond length is 138.3 picometers. Among all these three crystalline forms of the carbon, graphite is thermodynamically most stable allotropic form of carbon. The other examples which shows allotropy are phosphorus. White, red and black phosphorus are the allotropic forms of the phosphorus, and the allotropic forms of the sulfur are monoclinic, catina, plastic and orthorhombic sulfur. Now I'll give you a quick recapitulation via PowerPoint presentations. Allotropy is the existence of an element in two or more different physical forms which are almost chemically same. Allotropy with reference to carbon. Carbon exists in both crystalline and amorphous forms. Crystalline forms of carbon are diamond, graphite, fullerenes, which are discovered in 1985 by Kroto, Smalley and Curl and awarded Nobel Prize in 1996. Diamond has crystalline structure. Each carbon is in sp3 hybridized state and linked to 4 other carbon atoms in tetrahedral fashion. Carbon-carbon single bond length is 154 picometers. It has rigid 3-dimensional network of carbon atoms. Structure of diamond. The bonds are directional throughout the structure. Uses of diamond as jewelry, as an abrasive for sharpening hard tools, in making dyes, in manufacture of tungsten filaments for bulbs. Graphite, layered structure. Layers are held by van der Waals forces. Distance between the two layers is 340 picometer. Layer is composed of planar hexagonal rings of carbon atoms. Carbon-carbon single bond length is 141.5 picometers. Each carbon in hexagonal ring undergoes sp2 hybridization, making 3 sigma bonds with 3 neighboring carbon atoms. Structure of graphite. Structure: the fourth electron forms a pi bond. The electrons are delocalized over the whole sheet. Uses of graphite: conducts electricity, very soft and slippery, so used as lubricant in machines, in lead pencils, as electrodes. Fullerenes: prepared by heating graphite in an electric arc in the presence of inert gases such as helium and argon. Contains 60 to 350 carbon atoms or above. Pure form of carbon, cage-like molecules with shape like soccer ball and called Buckminster fullerene. Structure of fullerene: contains 20 6-membered rings and 12 5-membered rings. 6-membered ring is fused with a 6 or 5-membered ring, but a 5-membered ring is fused with only a 6-membered ring. Remaining electron at each carbon is delocalized and gives aromatic character to the molecule. This is the structure of Buckminster fullerene. Bond length between carbon atoms in double and the single bond lengths is 138.3 picometer and 143.5 picometer. Spherical fullerenes are also called buckyballs. Difference between diamond and graphite: diamond is one of the hardest substance. Graphite is one of the softest substance. Diamond is used as an abrasive. Graphite is used as a lubricant. Diamond, conductor of electricity. Graphite, excellent electrical insulator. Diamond has tetrahedral structure. Graphite, layer type structure. Diamond, naturally occurring thermal conductor. Graphite, used as thermal insulator. Diamond is transparent. Graphite is opaque. Amorphous forms of carbon: carbon black, coke, charcoal. Allotropic forms of sulfur. Structure of the sulfur molecule: S8. It is a crown-shaped molecule, a puckered ring. These are the sulfur rings. They arrange differently and form orthorhombic and monoclinic sulfur. Again sulfur, sulfur 8. Allotropes of phosphorus. These are phosphoric forms: red phosphorus, black phosphorus and white phosphorus. So dear students, you must have understood the concept of allotropy via various examples and through 3-dimensional structures and PowerPoint presentation.